Good morning, everyone. My name is Giovanni Chianese, and I'm going to talk to you about evaluation of crack front geometry by stream field classification using neural networks. In the context of experiments involving fatigue crack growth, it might be of interest to correlate the compliance measurement in the specimen with respect to the crack length. And for this reason, different standards have established relations to do so based on backface strain compliance. Based on 2D finite element analysis, assuming straight crack fronts. However, preliminary 3D FE analysis in our study revealed that normalized compliance evaluated based on measurement at backface, it deviates when crack tunneling occurs. Crack tunneling is the term for occurring of elliptical crack fronts or non-straight crack fronts. In this slide, you can see a plot with, on the y-axis, normalized compliance at the backface, calculated with 3D finite element analysis on the solid black line. And with the red lines, you have those with 3D finite element analysis. And in particular, you can see those with solid lines with the straight crack front agreeing, and with occurring of crack tunneling, the dotted and dashed lines, you can see that there's a deviation of the response. Additionally, standards prescribe the use of corrective factors in the case of crack tunneling exceeding 5%. For this reason, we pose the following research question. Is it possible to in situ monitor the crack propagation and crack front geometry based on strain measurements? And for this reason, we pose the following objective: to propose and validate a novel experimental technique that enables in situ analysis to simultaneously predict the crack front geometry and the crack length based on strain measurements. Our methodology is based on 3D finite element analysis of a CT specimen with occurrence of crack tunneling and the crack front modeled with arbitrary crack and an elliptical crack front with the center on the midplane of the specimen. Therefore, it is a 3 parameters model depending on the 2 radius of the ellipse and the length of the crack, which is measured on the lateral surface of the specimen in compliance with the laboratory practice to measure it with the microscope. The normalized crack length with respect to W is indicated as alpha, and the different crack fronts are simulated with by varying the radius R depth, because the radius R width was assumed in this study equal to 4 to effectively simulate the crack tunneling based on the geometry on the geometrical sides of the specimen we consider. Therefore, our objective is to establish a methodology to extrapolate normalized crack length and predict the crack tunneling condition based on the strain measurements. And in particular, we investigated two approaches. These approaches aim to be scaled in laboratory environment, and therefore they are the following. One is based on local measurement, which can be taken with strain gauges, and the results are fitted with functions. And the other is based on full field strain measurement with techniques such as the DIC, the digital image correlation, and the measurements are processed with convolutional neural networks. In particular, it is a problem that we aim to solve with the local measurement using two strain measurement, one at the back face and the other on the lateral surface, and different positions have been considered in these studies. However, the strain measured in the measured for different scenarios, they lead to strains measured at the two localization, which are linearly dependent, and therefore they do not provide independent information. This leads to non-unique solution of the problem, as indicated in this plot, where the points with the lines indicate different crack tunneling condition. They lie all in the same regions. For this reason, we decided to investigate an approach which uses stream fields in the X and the Y direction on the lateral surface. And they can be represented with matrix, which can be treated as two different channels of a figure, and the figure can be processed by convolutional neural networks. And the convolutional neural networks that we used derives from the ConvNet. This is a subplot of a subset of plots of the Y strain for different scenarios. You can see on the columns the normalized values of the normalized crack length. On the rows, you can see different crack tunneling conditions, and in particular, you can see that for each crack length, the beam shape increases its sides and bends over itself with increasing the severity of the crack tunneling. And this provides a reliable pattern for classification of the different scenarios. Additional information is provided by strain along the X direction. With this slide, I come to the result. We had therefore two tasks. We wanted to measure we wanted to predict the normalized crack length and the crack tunneling condition based on strain measurements on the lateral surface of the specimen. And they are respectively a regression task and a classification tasks. With respect to the regression of the crack length, our convolutional neural network have been able to do so with the root mean squared error of 0.02. And with respect to the prediction of the crack tunneling conditions, our neural networks have been able to predict it with an average accuracy of 91.75%. And details about this classification are provided in the confusion matrix, where each cell of the confusion matrix is reports the share of observation of each of the classes that was predicted with respect to the classes. Therefore, on the principal diagonal, you can see the share of correct classifications, whereas on the elements outside the diagonal, you can see the share of misclassifications. In particular, for beta equal to 0.05, we have basically a straight crack front. Beta equal to 0.8 is a not severe crack tunneling, which is a transition between the cases where a correction factor is needed or not, and the beta equal to 1 and 2, they are more severe condition of crack tunneling. The cases where straight crack front, the transition condition, are not misclassified with crack tunneling occurring, whereas only the cases with beta equal to 1 and 1.5 show a certain misclassification. However, there are those cases where the correction factor is needed. With this slide, I want to graphically summarize the methodology we propose and that we aim to scale to laboratory environment. First, we have the test and in situ a collection of strain measurements with DIC. Then we concatenate the strain along X and Y, and we input them to the neural network, the convolutional neural network. And finally, we predict alpha and beta, which respectively represent normalized crack length and the crack front crack tunneling condition. Next step of this work include the validation of this methodology with experiments in laboratory environment and extension of this methodology to more general cases. With this slide, I conclude my presentation. Thank you for your attention.